Hello everyone, welcome back. In the last class we started the discretization of continuous functions and their derivatives. So, we basically took a stencil, basically discretize our domain into number of grid points, took a stencil, it can be 3 point stencil, 2 point stencil, 5 point stencil and so on and so forth, and we can approximate our derivatives on that stencil. And we basically discretize using one sided formulation, two sided formulation, and we basically saw the properties, what are the errors and how the errors basically diminish as we go from one sided formulation to two sided formulation, or basically from the forward or backward differentiating to the central differentiating. Okay, and we talked about the discretization error and the round off error and so on and so forth. We also looked at the general discretization scheme, where we saw that for a given stencil, one sided or both sided, you can basically discretize your function and get the derivative, get approximation for your derivative. Okay. Today what we are going to do is basically see how the functions behave and the derivatives are captured using these different schemes, and then we will go to something called compact scheme. Okay. So, the compact scheme, as the name sounds, it is basically uses a compact stencil and gives you a better approximation of your derivative. Okay. So, we will look into those things today. To begin with, just recap quickly. Okay. So, for example, for the first order derivative, and if this is your point I plus 1, I minus 1, I plus 2, I minus 2 and so forth. Okay. This is uniform grid. Okay. So, this is x, this is x plus h, x plus 2 h, x minus h, x minus 2 h. Okay. So, you can write your backward differentiating in this way, or you can write f prime will be f I minus f I minus 1 by h, right. This is your backward differentiating, and we saw that the order of accuracy is 1. So, this is the first order accurate scheme. Similarly, you can have f prime using the forward scheme, forward differentiating scheme, become f I plus 1 minus f I by h, and this also will have the order h. This plus or minus does not matter. Okay, you can, I think it can be minus here. Okay, if you do the terrestrial approximation, but what we are interested is that with what power the error is going down. So, what is the power to the h? So, this n or delta x to the power n, whatever you want to use, the n is what matters, and that gives you the order of accuracy. Okay. Similarly, if you use the both sides central differentiating, let us say use I plus 1 and I minus 1. So, then you can write f I is equal to f I plus 1 minus f I minus 1 by 2 h, right. And we saw that this order of this scheme is h square, right. So, this actually matters a lot, because as we saw that let us say your h is equal to 0.01. So, in these two cases, in the first order cases, your error is of the order of your grid size, but if you go to the second order scheme, it goes, the error goes as h square, which is basically 10 power minus 4 for this size, right. And similarly, we also saw that using the generalized differential schemes, you can get higher order approximation also using the central differentiating, or you can have the one sided also. Okay. So, if you use I minus 2, I minus 1, I plus 1 and I plus 2, you can have this basically a f I plus 1 minus f I minus 1 by h, and plus b f I plus 2 minus f I minus 2 by h, and we found the value of a and b, okay, by comparing the different terms in the Taylor series on left and right hand side, different derivative terms. Okay. So, a we found to be 2 by 3 and b we found to be minus 1 by 12. Okay. So, these are some differential schemes that we have derived in the last class. We also derived the higher order scheme. For example, if you want to get del to f by del x square, which is the second order scheme, f double prime will be basically f I plus 1 minus 2 f I and plus f I minus 1 by h square, right. So, this is your second order term and this is also second order accurate scheme. Okay. Right. Now, let us see how these different derivatives behave. So, let us take a very simple sine function. Okay. So, between 0 to 2 pi. So, this is my 0 to 2 pi. Okay, and sine function would be something like this, right. So, we want to see how this function behaves. Okay, the derivative, we want to calculate the derivative of this. So, this is your f x, right. So, so of course, this is f x equal to sin x, right. So, then your f prime x will be cos x, right. So, this is what we know from the calculus, but here instead of using this formulation, what we are going to do, we are going to use 4 different approaches: the forward differentiating, backward differentiating, central differentiating, and the central differentiating 2 and central differentiating 4. Okay, as we saw in the last slide, all these 4 schemes. Okay, so basically, what we are going to do, we will make a mesh. So, here the mesh size is 0 to 2 pi, and we have taken the h is equal to 0.2, right. So, your mesh is, let us say this is 0 to 2 pi and then this is your h. Okay. So, each of these is basically equal to 0.2. So, you can get the number of grid points that you are getting. Okay. So, this is around 6.28. So, 6.28 by 0.2 would be around your number of grid points, okay, and maybe plus 1, right. So, if you try to, so now that you know the function is sin x, so you can get the sin x value at every discrete point, okay. And then once you get those value at sin of every discrete point, if you are using for the forward difference, okay. So, what you will do, you use sin x plus h minus sin x by h, right. So, this will give you the forward differentiating. Similarly, you can do the backward differentiating and other formulations that we discussed. So, if you do that, this is how your plot will look like. Okay, this is df by dx, okay, and this is against x, and you can see this goes up to 6.28, which is basically nothing but 2 pi, right. So, there is an actual curve, dot curve, which I do not know if you are able to see it. This is below the magenta line. Okay. So, basically both are overlapping. So, before that, just look at the forward differentiating. So, you can see the blue lines, these blue line curves that you see are basically the forward differentiating, and I will just make it little bold. So, this is your actual line. Okay, this is your actual line. Okay. So, you can see that this is slightly shifted on the left, okay, when you use the forward differentiating. On the other hand, if you use the backward differentiating, which is the green line, okay, this is slightly shifted to the right. Okay. The CD2 and CD4, they are basically nearly overlapping the actual cos x curve. Okay. So, if you now try to compare this with basically the error, if you want to take the error, okay. So, we want to see, because this is not very well visible here, how much is the error compared to the actual solution. So, what I have done here is this is the, so when you we are actually calculating f x, f prime x minus f prime x estimated. Okay. So, estimated using your finite difference scheme or central difference scheme or the schemes that you are using, and this is your actual value. Okay. So, if you see the blue line, okay, so that is your forward differentiating scheme. So, you can see that error is quite big, okay, and it becomes maximum around pi by 2, okay, and then here also at 3 pi by 2 you have the error very high. Okay. Similarly, if you use the backward differentiating scheme, so it also has the error, and you can notice one thing, that this error is kind of, one is going on the right side and other is going on the left side, right. So, in the last class we discussed that depending on the sign of the convection, okay, you may have one scheme stable and another scheme unstable. So, that is what you are seeing here. So, the blue one is left running and the green one is right running. Okay. So, the green one also shows the similar error here, which is basically the backward differentiating. Okay. If you look at the CD2, this the red line that you see here, okay, this line, okay, this is the error that you see. Okay. So, the error in the central differentiation, it becomes nearly 0 at pi by 2, okay, and maximum at 0, pi and 2 pi. Okay. Now, if you go to the CD4, okay, which is the fourth order central differentiation, okay, and you can see that in this particular case, these are the dotted points, okay, that you can see. These are the points which are basically on 0, right. So, the error is very low in the case of CD4. Okay. So, as you increase the order of accuracy, the error in approximating the derivative goes down. So, that is what we learned from this. Okay. So, we always strive to gain the maximum accuracy that we can. Okay. Of course, it comes at a cost, that if you are using CD4, your stencil size is big, that means you are using 5 stencil size. Okay. So, I plus 1, I plus 2, I minus 1 and I minus 2, right. So, stencil size is quite big, okay, if you are using let us say the CD4. So, their calculation also becomes little bit expensive, but at the same time it gives you more accuracy, right. Now, we will look at the compact schemes. This is also called the Padé schemes, okay. Padé schemes, okay, and also it has like a literature. So, initially by Sanjeeva Lele in Stanford had basically proposed these schemes. Of course, these schemes were not found to be stable at that point of time, and then people proposed filter to make these schemes stable. But right now, we are going to see that how these schemes are helping us in getting accuracy. We will talk about the stability a little bit later. Okay. So, before going to the implicit formulation, this is the general discretization approach that we had basically proposed, right. So, if you have points in I minus 1 and I plus 1, right. So, you can use this, and then you can use the symmetry also. So, if you are using this phi I prime, and if it is the scheme is of both sides of I, so you can use the symmetry, and then you can write it a phi I plus 1 and phi I minus 1 by h, and you can calculate the value of a. So, you can see that a is equal to minus 1 by 2 in this formulation this way, right. So, that will become phi I plus 1 minus phi I minus 1 by 2 h, right. Now, what if so here on the left hand side you have just one derivative that you are calculating at the point of I, okay, and then you are making use of this I minus 1 and I plus 1, right. What if you basically make use of stencil while calculating derivative? So, not only calculate at I, but also calculate at I minus 1 and I plus 1, okay, while you are keeping the stencil size same, right. So, you are making use of I plus 1, I and I minus 1 for calculating your functions, and at the same time you are also calculating the derivative at all 3 points. Okay. So, what we had earlier is phi I prime was basically a by 2 h, if I to write phi I plus 1 minus phi I minus 1, right. This is an explicit scheme, and here a becomes 1, right. If I want to solve it implicitly, that means I want to get the value of not only phi I prime, but also phi I minus 1 prime and phi I prime, okay, and we write our scheme in such a way that there is a alpha multiplying here on both the sides, right, phi I plus 1 and minus phi I minus 1, right. So, in this case you can see, if you look at the stencil, okay, so you are trying to calculate all 3 derivatives at the same time, I minus 1 and I plus 1, and that gives you an implicit system. So, how does it give you the implicit system? I will just show you in a minute, okay. And if you are using only I minus 1 and I plus 1, so this is the points that you have anyway on the right hand side, right. So, this is the explicit stencil because you have the functions known here, these are the implicit stencil because you are trying to calculate the function on this point and they are basically depending on left and right. Okay. So, just let me show you how basically it gives you the implicit system. So, I am sure many of you appreciate it already, those who have worked on the implicit schemes. If not, I am just going to derive it for you, okay, and show it to you that how it leads to an implicit system. Okay, so, my function is alpha phi I plus 1 prime plus phi I prime plus alpha phi I minus 1 prime is equal to a by 2 h phi I plus 1 minus phi I minus 1, right. This is, so if you take I equal to 1, right. So, this will become alpha phi 2 prime plus phi 1 prime plus alpha. So, this will be your boundary condition, right. So, if you have this I plus 1, I plus 2 and let us say we use 1 and n. Okay. So, these are my boundary points. You will have to give some boundary conditions here, okay, some boundary condition, or it can be a periodic thing. Okay. So, then we will start with I equal to 2. Okay. So, we will start with I equal to 2, right. So, this will be alpha phi 2 prime plus phi 1 prime, sorry, phi 3 prime plus phi 2 prime plus alpha phi 1 prime, which is coming from your boundary condition, right, will be a by 2 h phi 3 minus phi 1, right, and then phi 1 is also part of the boundary condition. Okay, let us say if you do I equal to 3, then this will be alpha phi 4 prime plus phi 3 prime plus alpha phi 2 prime will be a by 2 h phi 4 minus phi 2, right. So, similarly you can go on, okay, till the point of n minus 1, right. So, you can write it in as a system. So, we are solving plus phi 2 prime, phi 3 prime, phi 4 prime and so on and so forth will be basically a by 2 h, okay, and let us write the left hand side. Okay. So, if you look at this expression, so your alpha is multiplying the phi 3 prime, okay, and 1 is multiplying the phi 2 prime, and this is the part of boundary conditions. So, we are not going to write it. So, other things will be 0, all others will be 0, right. If you go to the next expression, this one, so now this is for 3. So, alpha is multiplying the phi 4 prime and your 1 is multiplying phi 3 prime and 2 is multiplying the phi 2 prime is multiplying alpha. Okay, so, this will become alpha 1 alpha and then all other things will be 0 0. Similarly, if you keep on going, okay, wait a second, this will be this will be 1 and alpha. Okay. I think I should have written in a different way. Okay. So, this phi 2 prime multiplies 1 and phi 3 prime multiplies alpha. So, this will become alpha 1 alpha. Okay. So, alpha phi 2 prime plus 1 phi 3 prime plus alpha phi 4 prime will is this one, and similarly you can keep on going like this, okay, 0 0 0, and you would see that it will lead to a banded matrix, which is basically a tridiagonal system, right. So, this will be alpha 1 alpha, alpha 1 alpha and so on and so forth, right. So, a will 1 will be in the diagonal and then all these terms next to the diagonal will be alpha, and then the rest of the terms will be 0. So, this will give you a banded matrix, a tridiagonal system, and similarly you can write on the right hand side. Okay. So, right hand side, if I write it in terms of phi 2, phi 3, phi 4 and so on and so forth all the way to phi n minus 1. Okay. So, you can see here this is phi 3 minus phi 1 and phi 1 is the boundary condition, right. So, this will just become 1, okay, and then you can sorry, this will become 0 and 1, right. 0 multiplied by phi 2 and others are, and rest all will be 0. and similarly you will have 1 0 sorry, minus 1 0 1 because there is a minus sign here, and this will go like this 0 minus 1 0 1, and the rest all term will be 0 0 0 minus 1 0 1, and this will go like this, and this will be a diagonal term, right. So, you can see that and of course, because of the boundary conditions there will be some more terms appearing on the right hand side on the first term and the last term. Okay. So, the first term will for example, this alpha phi 1 prime, okay, and minus phi 1 a by 2 h, right. These two terms will come here, and similarly there will be one term on the last term, right. If you have a periodic system, then you can just continue it like you have the matrix here, and the values will repeat. Okay. So, you can solve it as A x equal to b, right. This entire thing is b, this is A, and this is your x, and if you want to calculate x, that will be A inverse b, right. So, you can quickly see that it becomes an implicit system because you need to invert this matrix A, okay, or you have to, if you want to use it iteratively, you have to use some kind of tridiagonal matrix solver. So, you have algorithms like Thomas algorithms which can do this for you. If it were an explicit system, you can quickly note that all these of diagonal terms will go to 0, right, and this is an explicit system, right. So, if you want to calculate phi 2 prime, you can just use this value on the right hand side, you can calculate it. You do not need to invert a matrix. Similarly, you can do for phi 3 prime, phi 4 prime, and so on and so forth, because all other terms are 0, only the diagonal terms are present. Okay. But for the compact scheme, this leads to a tridiagonal system, okay, where matrix inversion needs to be done. So, this naturally more expensive, right. Now, let us try to see the parameters, right. So, we have seen the implicit stencil. Now, if we want to calculate the value of alpha in A, right. So, then only we can solve the system, these are the unknowns. So, we will use our good old approach, we will basically use the Taylor series. So, we have to do it for phi I plus 1, okay, and phi I minus 1, and apart from that, because we are also considering phi prime I minus 1 and phi prime I plus 1. So, we need to expand around phi prime I plus 1 and phi prime I minus 1 also, okay. And then what we have to do, that we have to compare coefficients of lowest order derivative, right. So, we can compare the value of phi I prime, and so on and so forth, right. So, if you compare because there is no phi I on the either side, so we will start with the phi I prime, okay. So, if you compare the coefficients of phi I prime, okay, so let me just do it for you, so that it becomes a, yeah. So, you have alpha phi I minus 1 prime plus phi I plus 1 prime, alpha will be A by 2 h, okay, phi I plus 1 and minus phi I minus 1, right. So, you can write phi I plus 1 will be phi I plus h phi prime I plus h square by factorial 2 phi I double prime plus h cube by factorial 3 phi I triple prime, and so on and so forth, right. And similarly, you have phi I minus 1 will be phi I minus h phi I prime plus h square by factorial 2 phi I double prime minus h cube by factorial 3 phi I triple prime, right. And similarly, you have phi I plus 1 prime will be phi I prime plus h phi I double prime, right, because we already have 1 prime here, okay, and then you have h square by factorial 2 phi I triple prime and plus h cube by factorial 3 phi I prime, and so on and so forth. And similarly, you have phi I minus 1 prime, okay. So, that will give you phi I prime minus h phi I double prime plus h square by factorial 2 phi I triple prime minus h cube by factorial 3 phi I 4 prime. Okay. Now, you have to multiply this by alpha, right, this both multiply by alpha, and this is basically a by 2 h, right, this both, this is a by 2 h and this is minus a by 2 h, right. And if you do that and you compare both the sides, so first thing you can compare is the phi I prime. So, what are the phi I primes on the left hand side, on the right hand side? So, if you look at this, okay, so this will be alpha, alpha is coming from here, okay, let me write like this. Okay, and this is alpha plus 1 and then again alpha plus alpha. So, this is on the phi I prime on the left side, okay, and on the right side you have a by 2 h, okay, and then you are taking 5 I plus 1, right. So, this will become, okay, so phi I plus 1, this will become h and minus h, okay, which is basically h plus h. So, this is nothing but, and this is phi I prime, right. So, this is 2 alpha plus 1 will become a by, so this is 2 h 2 h, this is v is equal to a. So, this is your first equation which I have written here, okay. So, 2 alpha plus 1 is equal to a. Similarly, now you can compare the triple derivative, okay. So, now you can compare the triple derivative phi I triple prime, okay, and once you compare that you will have again another expression between alpha and a, okay, and this is now here the factorial 3, okay. So, that will become, I think, alpha equal to a by 6 or so, okay, yeah, this will become alpha equal to a by 6. So, now you have two unknowns and two equations, you can solve these two equations and you get alpha equal to 1 by 4 and a equal to 3 by 2, right. So, your expression will look like, so alpha phi I minus 1 prime plus phi I prime plus alpha phi I plus 1 prime will be a by 2 h phi I plus 1 minus phi I minus 1, right. So, alpha value is 1 by 4. So, 1 by 4 phi I plus I minus 1 prime, okay. So, these are symmetric on both sides. So, does not matter, plus phi I prime plus 1 by 4 phi I plus 1 prime will be a is equal to 3 by 2. So, this will become 3 by 4 h phi I plus 1 and phi I minus 1, okay. So, you can write a little piece of code to basically solve these equations for phi I prime, phi I minus, I mean the entire system of equations of phi I prime, and when you invert it you basically can get the gradients everywhere, okay. So, similarly you can go for the higher order. So, I just want to show you some relations, okay. So, this is a simple sine function, okay. This is now it is sine 5 x, okay. So, the df by dx will be 5 cos 5 x, right, and I have taken 51 grid points and the distance is, I mean, 0 to 3 and 15 grid points. So, I am comparing the exact solution which is red and the CD2 which is blue and the compact 4 is basically black, okay. So, here it is not that visible, but you can see there is some difference here, okay. So, remember this both compact 4 and CD2 they are both done using I plus 1 and I minus 1, only 3 point stencil, okay. Yeah, one thing I forgot to mention here is that because we are comparing the third derivative, okay, to get the values. So, the next one will be the fourth derivative, okay, phi I to the 4 and your order of the accuracy will be the fourth order, okay. So, you can see the difference here, okay. It is not that noticeable in this particular case because this is a sin x function and it will become more noticeable, let us see if you reduce the number of grid points, but let us take some more complicated function. So, this is an exponential function which is derived like this, e to the power minus 35 x minus 0.5 square, and you can see this, not sure if you are able to notice here or not. So, there is a black and red, both are overlapping. So, basically compact scheme and exact are very similar, But if you use the CD2 scheme, which is the blue line, and you can see that there are some differences on here and here, okay, where there is a change. Okay. So, it is not able to give you a good approximation. Okay. Finally, if you look at the log scheme, okay, so this is the log scheme that I am showing here, and the red one is basically the exact formulation. Okay. The black one is the compact scheme, and the blue one is the CD2. Okay. And you can see that in terms of comparison, the compact scheme, the fourth order scheme is it predicts the value much closer, the derivative value much closer to the exact value compared to what you see from the CD2 scheme, right. So, and as I told you, both are using the 3-point extension only. So, naturally the compact schemes are basically giving you higher order of accuracy. Okay. So, in the next class we will see that how we can use this compact scheme to get even further higher order derivatives approximation. Okay. And we will also look at some of the difference scheme for non-uniform meshes. So, with that we will stop here and we will meet in the next class. Thank you.